Exercise Theory, Chapter 5, Exercise Physiology. We're going to start off talking this chapter with our cardiovascular system. It's also called the cardiorespiratory system because our cardiovascular system will deal with our circulation and our respiratory systems. So our heart, our blood vessels, as well as our lungs. So these two systems work together, and they are going to work to deliver oxygen and nutrients to the body. And so when we're exercising, they will get oxygen, nutrients to our working muscles. They will exchange the oxygen and nutrients at the muscle cells, and it will take away the waste products, especially carbon dioxide, which it will return to the lungs. The lungs will expel the carbon dioxide and bring in more oxygen. Now, the reason we talk so much about the cardiovascular system, it does work all the time. It's what keeps us alive. But exercise will specifically challenge these systems, because when we exercise, our need for oxygen at the working muscles goes up dramatically. Because it goes up dramatically, our heart and our lungs have to respond to meet these needs. The circulatory system is responsible for transporting materials through the entire body. So as I've mentioned already, it will transport nutrients, water, and oxygen, as well as the waste products such as carbon dioxide. So oxygen is going to the working muscles and to the tissues of the body, and carbon dioxide is brought away from. So here is a general picture of our circulatory system. What you are going to be looking at here is the heart, as well as the arteries and veins. You'll notice the heart in the center. You can see that it's 4 chambers. You have a right and a left side of the heart. Those are different systems that pump blood in different directions. You'll also notice on the diagram that at the chest level, the level of the lungs, you're seeing a series of endings of arteries and veins, and those are the ones that are going to the heart, to the lungs, for the pulmonary circulation. So that it's going to take the blood to the lungs to drop off carbon dioxide and to pick up more oxygen. So let's do a little talk while we have a diagram in front of us, and I encourage you, please have your textbook open and ready to go, because in the next few slides we'll continue talking about this system, but you may not always have a visual to refer to. I find it works much better if you can see a picture while you're hearing the words. So looking at the heart, you can see that there's 4 chambers. The last chamber is covered a little bit by your aorta, so it's a little harder to see. But what will happen is blood will come from the body, and it'll come into your right atrium. Your right atrium is in the top left corner of the heart diagram, because you have to remember we're talking it right as it's on the right side of the person whose heart it belongs to. So on the top left corner is your right atrium. The blood will come from the body. This is going to be blood that does not have much oxygen left in it because it's returning to the body with carbon dioxide. It's returning via veins. It will go into your right atrium and then get pushed down into your right ventricle. The ventricles are the 2 chambers on the bottom of the heart. The atria, or the individually atrium, are the top chambers in the heart. So it will go from the right atrium to the right ventricle, and that right ventricle will contract, and it will send that deoxygenated blood, so blood without oxygen, to the lungs. In the lungs, on its way to the lungs, it is going to go from arteries to arterioles, down to our smallest blood vessel, which are capillaries. These capillaries will come into contact with the alveoli, which are little air sacs in the lungs. So again, the capillaries will come into contact with the alveoli in the lungs. The blood from the capillaries will dump carbon dioxide into the lungs, and it will pick up oxygen. And it does this for multiple purposes, or multiple reasons. It has to do with pressure gradients and concentration gradients, and how hemoglobin will act at the lungs. So once again, at the lungs, a capillary will come into contact with an alveoli, the smallest of the vessels and the smallest of the cells of the lungs, and the circulatory system, so the capillaries will dump carbon dioxide into the lungs and pick up oxygen. The capillaries then become bigger and they become venules, and then they become larger again and become veins, and that vein will return with oxygenated blood to the heart. This time it will return to the left atrium, and that's the square that's the hardest to see. So in this diagram of the heart, it would be pretty much the upmost chamber. Okay, so it's your left atrium, and it'll get pushed into your left ventricle. Now remember, this is stuff that's returning from the lungs, so there's lots of oxygen in this blood. That left ventricle will contract. Blood will exit the heart through the largest of the arteries, which is your aorta. You'll hear them talk about your aorta. From there, it'll get pushed into more and more arteries, and the arteries will gradually get smaller. They'll look like branches, gradually getting smaller. So it goes to more and more arteries until it goes to arterioles, which are very small arteries, and then it goes into capillaries. Capillaries are very, very thin-celled, so they're single-celled. They're single-celled walls, and this is going to now allow gas exchange to occur at the muscle tissues. So at the muscle tissues, the blood, which has oxygen in it, will push oxygen out into the muscle tissue, and the muscle tissue in turn will dump carbon dioxide into the blood. So at the capillaries, at the muscle fibers, we will be getting rid of oxygen to give oxygen to the working muscles and picking up the waste material of carbon dioxide. So this occurs at the capillaries. At the end of the capillary bed, you reach the venules again, and then they'll get bigger and bigger until you're back into the veins. These will travel back to the heart. You'll have the superior vena cava and the inferior vena cava. These are just the largest veins as they arrive at the heart. They are carrying deoxygenated blood because it's blood returning from the body. They will go into your right atrium, into your right ventricle, which is deoxygenated blood. The right ventricle will contract, and it will send that deoxygenated blood to the arteries that are going to the heart, the pulmonary artery, or no, the heart, pardon me, to the lungs. So they're going to go into the pulmonary arteries towards the lungs, to the pulmonary arterioles, to the capillaries to do gas exchange with the alveoli of the lungs. So the capillaries will dump carbon dioxide into the lungs, pick up more oxygen. It will loop back to the heart through the venules, through veins. So when it reaches the pulmonary veins, it will end up landing in the left atrium with oxygenated blood, move into the left ventricle, and then the left ventricle will contract, sending the blood through your aorta into your arteries. This is all oxygenated blood. Arteries will move into arterioles, which will reach capillary beds, which are thin-celled walls. So the carbon dioxide and oxygen will exchange at these capillaries in the muscle fiber. We will dump the oxygen to the muscle fiber, pick up carbon dioxide, then we'll move into venules, veins, the inferior or superior vena cava, back to the heart. So what's really happening here? Any vessel that leaves the heart is always an artery. So you always will move from an artery to an arteriole to capillaries to venules, veins, and back to the heart. So the venules and veins are always what are returning blood to the heart. The capillaries are always where we have gas exchange, either at the lungs or the tissues of the body. Other things to kind of note is your right hand circulation is your pulmonary circulation, and it takes deoxygenated blood to the lungs. It picks up oxygen and returns it to the heart to go into the left side of the heart to go into your circulatory system, so it gets sent to the body. So when I picture the heart and the circulatory system and the pulmonary circulation, I picture loops. So there's a small loop from that right side that's going to go collect blood from the lungs, return to the left side, and then that one does a big loop through the body, returning to the right side again. We're going to talk a lot about this. I want to give you this general overview, and now I'm going to point all these things out individually. So here's just a diagram of what we just talked about. So now you'll see it all listed. There's your right atrium and right ventricle, and the left atrium is just a little harder to see, and the left ventricle. Remember, the deoxygenated blood returns from the body through the veins into your right atrium, gets pushed into your right ventricle, and the right ventricle is going to serve as a pump to send that deoxygenated blood through the pulmonary arteries to the lungs. It will pick up oxygen in the lungs and dump off carbon dioxide. It will return back with oxygenated blood to the left side of the heart, the left atrium, into the left ventricle, and the left ventricle is what's going to give it a large contraction and send blood out through your aorta, through the body, through your arteries, your arteries. Gas exchange will occur at your capillaries and muscle tissues, go to venules, back to veins, back to the heart. So here it's just saying that the heart acts as two separate pumps. The left side will pump the oxygen-rich or oxygenated blood through to the tissues of the body. This is your systemic circulation. The right side pumps oxygen-depleted or deoxygenated blood through the lungs, which is our pulmonary circulation. So this is just repeating what we've already said, so this should now be review for you. Deoxygenated blood enters the heart from the body, enters into the right atrium. It'll actually move from the right atrium to the right ventricle. The right ventricle will contract and push that deoxygenated blood to the lungs. In the lungs, the blood is oxygenated and returns to the heart through the pulmonary veins into the left atrium. It'll move from the left atrium into the left ventricle. The left ventricle will serve as the pump, and it will pump it out through the arteries, and then it'll return back to the body through the veins after gas exchange has occurred. So arteries always leave the heart, veins always return to the heart. So what makes the heart beat? It's actually part of our autonomic nervous system. So this system is systems that work involuntary. So we don't have to remind ourselves to beat our heart. We don't have to be like, oh, contract, contract, contract. Skeletal muscle that we talked about, that's voluntary. We can choose to contract or relax our skeletal muscles, but the heart will happen automatically, and it's actually got its own conduction system that you don't really need to worry about. It happens on its own, and that electrical stimulus will cause those ventricles to contract to drive blood throughout the body. So let's just continue looking at these different things we've already spoken of. So the blood will leave the heart, blood leaves the heart with oxygen through the aorta, and that is the largest artery in the body, and then it branches into smaller and smaller arteries, okay, and it'll keep branching down until it reaches the arterioles. It's important to note that the walls of the artery are thick and elastic, so this is why we can feel a pulse. When you feel your pulse, you're actually feeling a bolus of blood that was ejected from the heart pushed through that artery. And when it pushes through that artery, it stretches and you get an elastic recoil. That's what you're feeling, the pulse. Because when your heart sends blood out, it sends it out in waves, and that gives us our pulse. So the walls of the artery being elastic will enable them to expand to accommodate the volume of blood expelled in surges from the heart. And then during relaxation of the heart, so in between the beats, the elastic recoil of that artery will force the blood forward. Okay, so remember, arteries have elastic in them. They will stretch out as the bolus and surge of blood comes to it, and then it will elastic recoil, sending the blood forward. This is how we move blood along. So we're going to be going from arteries to arterioles. This just means small artery. And into that we go into our capillaries. And we'll talk about these as capillary beds. So they're thin-walled vessels. They're single-celled vessels, and they will permit the exchange of gases and nutrients between the blood and the tissues. Okay? We will call this the microcirculation. After this exchange has occurred, the blood keeps moving through those capillary beds and will return to venules, which are very, very small veins, and carry on to the veins, returning to the heart. So in your systemic circulation, the blood will drop off oxygen and pick up carbon dioxide because it's interacting with muscle fibers and organs. In your pulmonary circulation, it does the opposite. So that's where you're taking the deoxygenated blood to the heart. You're dumping off carbon dioxide through your capillaries and picking up oxygen. So veins. After the blood has flown through that arterial network and through the capillaries, there's a collection system that will return it to the heart, okay, the blood to the heart. And this is our venous return. Veins have thin walls, so they're not able to push blood as effectively. What is unique about veins is that they actually have a one-way valve, and we will see a better diagram of this. But as the blood is pushed up, you have these valves that will close to prevent the blood from falling back down towards your feet or hands. So the blood gets pushed up, and then it's prevented from falling back down. These valves can be faulty, and that's where you get varicose veins from. So when you have people have that bulging in their vein, especially in their calves, you usually see varicose veins. That is just the valves didn't function properly, and it's allowing blood to pool in those veins. This is a really nice picture. So this is a vein returning with blood cells up to the heart. And as you can see, when the blood goes up, those valves will push through the valves, and the valves will close, so it can't fall back down. So what happens when we're at rest, our heart beats slower, and so our body is able to easily return. The pressure from that artery system will give enough push to push things through our veins as well. When we exercise, our demand for oxygen at our working muscles will increase, so our heart rate will increase. So our heart rate will start to beat quickly. It'll send blood to the capillaries. And because we're moving and we're doing movement when we exercise, what will happen is our contracting muscles will squeeze and milk the blood back up the veins. So muscular contractions will help drive that blood up towards the heart. Okay, so it'll cause a milking kind of action. So that works wonderfully. So we're exercising, our heart's beating very fast, we're helping return blood to our heart because we are doing movement of our muscles. What happens when we stop exercising suddenly? So let's say you're jogging, you're running really fast, and then you stop, and you completely stop. Your heart's still beating quickly, so it's able to quickly send the blood out to the working muscles. And it does that very, very quickly, very rapidly. But now that you're not moving, then the blood is not being pushed back to the heart with the contraction of the muscles. So the muscles are no longer contracting because you stopped. The blood all pools in the extremity. So when the blood pooling occurs, it'll cause a decrease in your blood pressure that's perceived right at the heart. Because the body doesn't realize that what's really going on, it doesn't realize that, oh, well, the blood's just in the extremity, the body is going to assume that you have a problem with your blood pressure, and that what it will do is it will give you a burst of adrenaline, that's norepinephrine, adrenaline, to boost your heart up. Right? So it's going, oh, blood pressure is really, really low. We need a boost to the heart to increase our blood pressure. So it will give norepinephrine, also known as adrenaline, a big jolt to the heart. This is where people can have cardiac incidents. This is where they can run into trouble and have heart attacks or trigger issues. So see, once again, when you exercised, the movement helped return blood to the heart. If you stop too suddenly, the heart's still beating very quickly, blood will pool, your body will detect a decrease in blood pressure around the heart because the blood's now all in the extremities. It will give a burst of adrenaline, or norepinephrine is the term they're using here, that will try to jolt the heart to increase the blood pressure. If the person is prone or susceptible to any kind of heart issue, this can result in something very, very negative occurring. If we do a nice normal cool down, so if instead of stopping suddenly, we decrease the intensity of our movement, so say we were running, we go from running to walking, well, our muscles are still moving. They're still milking that blood back to the heart. And as a result, the muscles help return the blood to the heart. As the heart slows down, the heart will slow down gradually. You do continue to do movement, and then everything will normalize. You won't have this problem. So carrying on, it just says that this high level norepinephrine can cause cardiac problems for some individuals. And we prevent this by keeping your participants moving after that higher intensity cardiovascular portion of the class. So we do a proper cool down. This is why a cardiovascular cool down is so important. It is there to prevent venous pooling or blood pooling. So next we have the respiratory system. This is how we're going to take oxygen into the body so that the circulatory system can pick it up and send it through the body. So we take air in through the nose. It's going to go into the pharynx, the larynx, the trachea, into the bronchus, and into the lungs themselves. So the respiratory system, so the purpose of this system is to provide a means of supplying oxygen and removing carbon dioxide. So we inhale oxygen, and then we are going to move that oxygen down through our lungs into our alveoli. Alveoli are the smallest cells in the lungs, and the capillaries from the circulatory system are going to allow gas exchange. So pulmonary ventilation is the process of moving air in and around the lungs. Air enters through the mouth or nose, passes the pharynx and the trachea. Beyond the trachea, it's going to divide into the bronchi and then further divide into bronchioles. And these bronchioles are going to divide into alveoli. There you can see the word alveoli, which are tiny sacs that are surrounded by tiny blood vessels, which are your capillaries. Now, the reason this all works, and I've already kind of alluded to this, is that oxygen is going to be moving from areas of high pressure or high concentration into areas of low pressure or low concentration. So in the case of the lungs, it's going to move, you have inhaled in oxygen, so the pressure and the concentration of oxygen within the alveoli is high. Because the capillaries are returning blood that has carbon dioxide, the volume and pressure and concentration of oxygen in the capillaries is low. So blood will enter from the alveoli, or oxygen will go from the alveoli into your capillaries at the lungs. Hemoglobin is what we're going to attach that oxygen to transport it throughout the body. It's worth mentioning too, we have something called our ventilatory threshold. Our ventilatory threshold is the intensity of exercise above which your breathing becomes labored and you feel like you cannot draw in as much air as your body wants. So the demands of oxygen at your working muscle increase so high that you have to start breathing very rapidly. You're trying to rapidly do gas exchange, and you get to a point that the amount of lactate buildup in the working muscles increases so high that it's going to change the acidity in the body. So you're trying to breathe off enough acidity to change the acidity within the body, and as a result, you find you can no longer breathe. So the ventilatory threshold is closely linked with your lactate threshold. Okay, the amount of lactate in the body. And just like the breathing rate, your blood lactate concentration can increase gradually, and then all of a sudden it increases much more rapidly, which is your ventilatory threshold. So it is, since we understand how important oxygen is to our working muscles, it allows us to produce activity and where it's necessary for life. It's important to note too what can reduce the amount of oxygen in the blood. And this is where iron plays a huge role. So I'm sure most of you have heard about problems with iron-related deficiencies. And the iron is going to be important with the hemoglobin. And so if for some reason you don't have as much iron in your blood as you should have, It's going to affect your hemoglobin levels, which will affect how much oxygen you can transport in your body. And individuals that may have an issue getting enough iron in their diet are going to be especially women who might eat poor diets, that are endurance athletes, that experience heavy menstrual flows. They might have lower iron levels afterwards, are pregnant or breastfeeding. Those individuals have issues with iron levels, or are vegetarian. I'd highly recommend, if you have reasons to suspect that somebody has low iron levels, send them to their medical doctor. Let their medical doctor do blood work. It's not really recommended just to up and start taking more iron. It's not always a desirable thing. So you do want to let a medical doctor control this, because perhaps they're fatigued, because usually people with low iron levels will experience a great deal of fatigue. They become anemic and they are absolutely exhausted. And so you really want to confirm that is the real reason, okay? But be aware of these individuals. So if you do have a lady, a female, who is an endurance athlete, you want to make sure that they have a full, complete diet. If they are vegetarian, you want to make sure that they are taking in natural sources of iron to decrease the likelihood of having iron deficiencies. However, if it progresses beyond something that can be naturally supplemented with food, please send them to a medical doctor. So I've already mentioned this gas exchange. This gives us a nice picture of it, however. So what you're looking at in the picture are the alveoli. So it's a singular alveolus, and that is the smallest cell that you'd end up finding in the lungs, okay, the smallest unit. And running along beside it is a capillary from a capillary bed. So the alveoli will have oxygen in them. The capillary will have carbon dioxide, and they will exchange, where the alveoli will pick up the carbon dioxide and the capillary will pick up the oxygen. The capillary will turn the oxygen to the heart, where it will get pumped out in your systemic circulation, whereas the alveoli will take that carbon dioxide and you will exhale it. At the tissue cells, it moves in the opposite direction. So that capillary arrives at the tissue cells and it will have oxygen in it. The tissue cells will have a buildup of carbon dioxide, and the oxygen will move from the capillary into the muscle tissue, and then the muscle tissue will dump carbon dioxide into the capillary. So gas exchange is a process in respiration involving the unloading of oxygen and the loading of carbon dioxide at the tissue level for a return journey to the heart, which will then go to the lungs. In the muscle, which uses a lot of oxygen during contraction, a rich capillary supply, so that means a rich capillary bed, there's a great deal of capillaries, surround each muscle fiber. At the muscle level, the oxygen diffuses from the red blood cell through the capillary membrane into the muscle cell. And because the oxygen is going to move from an area of high pressure or high concentration to an area of low pressure or low concentration. Because at the tissue cell, the amount of oxygen in the capillaries is high, and in the muscle tissues it's low, that allows this movement. And the transport of oxygen is the reverse process. This all gets reversed at the lungs. So let's just make a moment to talk about the Valsalva maneuver. The Valsalva maneuver is a breath-holding maneuver, and it's where an individual will take a deep breath in, they'll fill up their lungs, they'll compress their abdominals, and they'll close their throat off. And they'll close the throat off, so they will forcibly hold their breath. Now, I'd like to point out that there is a purpose and a reason for performing the Valsalva maneuver. When people are lifting extremely heavy weight, they perform the Valsalva maneuver to give greater stability to their spine. So it usually sees it with deadlifts and squats, sometimes a little bit with extremely heavy bench press. So they're not doing a Valsalva maneuver for bicep curls. They're doing it for these very large movements where they need to brace and bear down on their abdominal contents to stabilize their spine. So that's a Valsalva maneuver. The Valsalva maneuver is not simply holding your breath and not breathing, but rather it's purposely taking air in to fill up the lungs to increase the thoracic pressure, which will increase abdominal pressure, that with a contraction of the abdominal muscles will stabilize the spine. It involves closing off the throat. This maneuver is used for very advanced individuals. it still can cause an extreme high spike in blood pressure, which can be undesirable, especially for people with health problems. To go through life-saving Valsalva maneuver is bad and horrible. No one should do it. That would make you look foolish to completely say that. However, for the vast majority of the population, we do not lift heavy enough weights that we require the Valsalva maneuver. There are negative side effects to the Valsalva maneuver, which is that high spike in blood pressure, and also because of the intrathoracic pressure, so the pressure in your thoracic cage will go up, which will make it difficult for blood to return to the heart. There are negative side effects to the Valsalva maneuver. So for the majority of individuals that you will ever come across, you are not recommending the Valsalva maneuver. They will not be lifting heavy enough weights that they need to brace that hard. Where we also get confusion is that some people confuse Valsalva maneuver simply with breath holding. We never recommend that you would just simply randomly hold your breath when doing an exercise. Beginners you see will do this. You know, they're focusing so much on the exercise that they unintentionally hold their breath while doing it. So people will ask, when am I supposed to breathe during an exercise? The recommendation is to tell them to continue breathing. They must keep breathing. And what we usually recommend you do, you breathe during the work phase. So as you are lifting the weight, you exhale. You inhale as you lower the weight back down. So when you do the concentric muscle action, the lifting, the work phase, you will exhale, and then you'll inhale during the eccentric or lowering phase. All right, so once again, Valsalva maneuver is used with extremely advanced individuals. For the most part, these individuals will be outside of your scope of practice. You don't do the Valsalva maneuver in a group class. This is for power lifters, Olympic lifters. And so most of them will be outside of your scope of practice. So all of the rest of your participants should be breathing all the time. You never want to encourage somebody to hold their breath, because if they might have a cardiac incident, they might pass out because of the lack of blood flow to the heart and to the brain. You encourage them to breathe. They exhale during the concentric or work phase, inhale during the eccentric or lowering phase. So since we're talking about breathing, you should be aware that there are things that can affect how rapidly somebody breathes. One could be posture. So if you're sitting there right now, slump over and slouch down in your chair. You'll notice how much harder it is to breathe. Okay, so it's going to make it more challenging to breathe. You won't be able to do quite as full of breaths. So be aware of this, because especially with spin classes, if somebody's all leaned over and slumped over in the spin class or the cycling class, pardon me, this can cause issues with breathing. Also, stimulants will speed up your respiration. So caffeine, nicotine, anything like that. So somebody's drinking a bunch of coffee or smoking right before they come into class, which ideally they're not doing, it's going to increase their respiratory rate. Sedatives do the opposite. So sleeping pills, alcohol will decrease their breathing rate. And the last thing is a medical condition. It's called emphysema. Emphysema, when you saw those alveolar sacs, what happens is they get damaged. So you have fewer alveolar sacs, and so it's harder to get oxygen to the blood because you're lacking the alveolar sacs, which will allow the exchange to occur. So emphysema, people that experience emphysema, they breathe heavy at very light effort. In fact, you'll often see them seated, breathing heavy.